So yesterday, Google Quantum AI published a 57-page white paper with co-authors from the Ethereum Foundation and Stanford at the same time. And the core finding is that the quantum computer needed to break Bitcoin and Ethereum's cryptography is about 20 times smaller than anyone previously estimated. But what really sets this apart from any other quantum scare piece is that this is published in a zero-knowledge proof alongside it. And that basically means that a cryptographic receipt proving that their math actually works and proving that they know how to build the attack without showing anyone how to replicate it. That's never been done before for a quantum vulnerability disclosure. The paper is co-authored by Google Quantum AI, the Ethereum's Foundation, and Stanford. It's about 57 pages. And buried in it are a handful of findings that I think pretty much are an interesting focus for security timelines going forward. The setup here is that every major blockchain, Bitcoin, Ethereum, Solana, and basically all of them, relies on the same underlying math to keep your funds safe. It's called an elliptic curve cryptography, and the reason that nobody can figure out your private key from your public key is that the math problem sitting between them is absurdly hard to solve on a normal computer. So quantum computers change that because there's an algorithm called Shor's algorithm that can solve it efficiently, and that's been known since the 1990s. So the question has always been just about scale. How big does the quantum computer actually need to be? And previously, it was assumed to be very large. So the previous best answer was from published research was about 9 million physical qubits, and Google just brought that down to fewer than 500,000. It's roughly a 20x reduction in the hardware required to break the cryptography that essentially secures all of crypto. And that single number is really the headline of this paper. So nobody has 500,000 qubits today, and that's the largest machines are still in the low thousands, which is a pattern that the paper highlights that's hard to ignore. Every few years, the estimated costs of these attacks drops by an order of magnitude. And it's not because the hardware got dramatically bigger, and it's not because the algorithms and the error correction techniques got any better. It's that the target keeps on moving closer when the machines stay roughly the same size. And there's a line in the paper that stuck with me because they argue that they'll be able to publicly demonstrate breaking even a small elliptic curve, a 32-bit version. It may be already too late to start migrating. The reason that jump is from breaking a small curve to breaking the real 256-bit one isn't a gradual climb. It's a series of engineering thresholds and one that clears. Good thing is that this is where the paper gets really concrete. Google's team of pretty much estimates that a superconducting quantum computer, which is the type Google itself is building through its own labs, the attack could execute it in about 9 minutes to break the algorithm for what they called a prime state, where the machine has already pre-computed part of that algorithm. And the reason that number matters so much is that Bitcoin's average block time is 10 minutes. And what that means is that in practice, a quantum computer could technically intercept your Bitcoin transaction while it's sitting and waiting to be conserved. Under this, when you broadcast your public Bitcoin transaction, your public key becomes visible to the network and the attacker is able to derive your private key, forging a competing transaction and redirecting your Bitcoin to a different wallet before your funds go through. So this paper refers to it as an on-spend attack. And the underlying model is that the probability of success against Bitcoin is roughly 41%, which is decently high. Against Litecoin with its 2.5-minute blocks, it drops under 3%, and against Dogecoin at 1 minute, it's less than 1 in 8,000. And against Solana, it's at 400 milliseconds. It's essentially zero. So block time, this parameter that pretty much most people think of purely in terms of user experience and throughput, turns out to be also a quantum security parameter, and that reframe is going to matter a lot going forward. So about 1.7 million Bitcoins sit in the oldest address type on the network, which is paid to public key. And these are from the Satoshi era, where the public keys are literally just sitting on a blockchain without any hash protection. So everyone has always known that these were the most exposed coins on the network, and that's old news. But what's not old news, though, and this is what kind of making this paper go viral, is what they say about Taproot. P2, Bitcoin's newest address standard that the community adopted in 2021 as a significant technical upgrade, also stores the public key directly on chain, and the paper explicitly calls it a security regression. Bitcoin's most modern transaction volume reintroduced the same quantum vulnerability class as its very old one. And this isn't an edge case. In this case, Taproot moved from over 16 million Bitcoin in 2025 and accounted for over more than a fifth of all Bitcoin transactions. So it's actively being used as a massive scale, with carrying its exposure with quantum attacks. Currently, out of the 20 million Bitcoin or so in circulation, there is about 6.9 million Bitcoin that can be attacked via these quantum attacks. The one thing that the paper is very clear about, though, is that Bitcoin and this paper are discussed together, and the paper is very clear that proof of work mining is not threatened, and that Grover's algorithm gives a theoretical speed up for hash searching, but the error correction overhead makes a quantum miner's orders of magnitude slower than a community ASIC. Bitcoin's exposure is mostly about address type and key management, and while it's serious, it is relatively contained. So the larger problem that this paper brings up is not a massive problem that's going to hit immediately. So everyone's Bitcoin is safe. But Ethereum is fundamentally different in this situation, and that pretty much jumped out most to me within this paper. The Ethereum platform is the stablecoin and DeFi protocol that actually works under the hood of a lot of financial platforms. There's a smart contract holding or referencing real value and oftentimes billions of dollars worth of value. And almost always there's an admin key behind it, an externally owned account controlled by a single private key that can pause a contract, upgrades its logic, freeze accounts, or move funds. Under a hypothetical quantum scenario, essentially quantum can possibly, at this moment, interrupt the process for all the things that are tokenized on chain. So Tether is tokenized and so forth. So to have a ton of stablecoins on chain is, it comes with its own quirks. All of it is sitting behind admin keys protected by quantum vulnerable cryptography, which is changing right now as the market speaks. To crack with 5 distinct attack services, all exploitable at rest attacks, the top 1,000 Ethereum accounts would take a fast clock quantum computer less than about 9 days to crack all of them. And those accounts, the top 1,000, all hold about 20.5 million ETH. So given that what we've walked through, the natural question is who is doing something about this? So in the paper specifically, they call out Algorand, XRP, Ledger, and Solana as some of the chains that have already started experimental deployments, and a handful of smaller chains as well. The paper also goes out of its way to prove that Bitcoin's proof of work is safe, and that Zcash's newest shielded protocol is resilient against quantum attacks on its protocol parameters, and that public keys hidden behind hash functions on many chains are as protected from at-rest attacks, and the address cannot be reused. Ultimately, the chains that start the migration before anything bad happens are the ones that are going to be in a fundamentally different position than the ones that try to do it under pressure. The last section of this paper is the one that I pretty much keep on coming back to, and I think it might be probably the most consequential of them all. There are 1.7 million Bitcoin sitting in old peer-to-peer addresses that will never be migrated to post-quantum cryptography. Not because the community won't try, and not because the owners are gone and the keys are lost. There's just simply a fixed target sitting on a public ledger, and eventually somebody is going to build a quantum computer large enough to derive every single one of those private keys. Google, in the paper though, proposes a strategy where governments form a digital salvage strategy. And the analogy they draw to it is pretty much to maritime salvage law. So the legal regime that is maritime salvage is very old, and essentially it's governed the recovery of sunken treasure for centuries. So the idea is that it's regulated recovery with taxable gains and clear jurisdictional rules, rather than a free-for-all where whoever builds the first capable quantum computer just takes everything. The alternative, however, is that they lay out that without any legal framework, these assets get seized by whoever gets there first, and whether that's criminal organizations, hostile nation states, or unregulated actors operating outside any jurisdiction with hundreds of billions of dollars flowing outside the formal economy. The takeaway from this paper, though, is that crypto is completely fine. The only thing is that the timelines for shifting post-quantum are becoming shorter and shorter, probably a lot faster than a lot of people presumed. So people would have had a presumption that quantum was more of a 2033 threat. Now more people believe it's a 2030 threat. Thank you.